So let's cover one other thing here. This is the last class. So this is the last one we're doing. We are going to cover today Fearless Concurrency, Chapter 6. We'll finish 15. I'll go on the assumption that we didn't finish it last time. After Fearless Concurrency, there's Object-Oriented Programming. That is to speak to people who previously come from OO languages and they want to see what those patterns look like in Rust and how we work around some of those things. Patterns and matching, Chapter 18 is useful. The refutability part is interesting because it talks about this concept of deconstruction, and when you take something apart, you have to effectively be able to match its shape. So those concepts are introduced there. Basically, there's methods of doing things in Rust, and in order to do them to be type safe, you have to know your pattern matches. So the act of knowing when your pattern matches is this concept called refutability. The advanced features are just that. I think that the unsafe Rust is probably not that important. The others are probably a little bit more important. And then the final project is building the multi-threaded web server. So hopefully we get done with all of Chapter 16 today.
How many more weeks of Rust do you anticipate?
This is it. This is the last one. This is the last one. Yeah.
Evan has rage quit. He's not doing it anymore.
Well, we said we're going to do 10. So we did 9 and got hit by a hurricane. We swung the 10th one over. Then we're done. But yeah, I mean, after this, we can start talking about whether or not we want to do other things like Kubernetes or Helm or something different, you know. And not to mention, if anyone wants to continue on with Rust, they can always bring their questions up and we'll help them out, what the group's about.
Make a day of it.
All right, so reference cycles can leak memory. So when we did this, we hit on a bunch of different concepts and we kind of iterated through them and talked about where the problems were with those implementations. In 15.1, we did this whole using box T to point to data on the heap. So we effectively made an implementation of a list, and that list was done with boxes. And the problem we were solving with boxes was that when we didn't use a box, we didn't know how big the list was, because the list is recursive in nature. So we're creating a type that was recursive in nature. And the problem with a type that is recursive in nature is that you don't know how big the size is of it. So you don't know whether or not it can fit on the stack at all. And that doesn't work because Rust is a strongly typed language. So what we had to do in order to get around that was we had to give the type a static size. And we gave it a static size by breaking the recursion. And we broke the recursion by saying that a list is one element and then a box of another list, right? Now suddenly we are not defining it as one element and another list. We're defining it as an element and a box of another list. And because we did that, we know how big the box of another list is, right? It's the size of the pointer to the rest of that list. So this allowed us to create a list of indefinite size, but we weren't allowed to have circles, right? We couldn't have circular lists. They had to be a list where we start on one side and we go to the end. And we worked on fixing that, right? Then we got into the rectangular references with the deref trait. And here we were just showing that, let me make sure we're on the right one here. Yeah, okay. So here we were showing that we can create our own custom box type, and then that custom box type had the ability to dereference it as if it was an actual reference, a pointer. And the reason was because there's a blanket implementation for deref. So that deref applied to all implementations of box. And this is what we did here. We implemented this guy. And this said that for anything we dereference, we just want to pull off the element inside. And that worked for us. So we were just showing an easy copy of deref. And we talked about why we needed that. We need that because we want to provide a better syntax than something like this, where we're having to do that manually. So we can teach Rust to do that automatically, and then it's substantially easier. And then we did the drop trait. And remember, the thing about the drop trait is the drop trait has a method .drop on it, and Rust has chosen not to allow you to use that method. So there is a method there that we could call, but we don't call it. We only allow Rust to call that method. So if we wish to call it, we have to use drop in stdmem. And that allows us to forcefully drop something. Of course, all of your same memory semantics are there. If you drop it, you can't use it afterward because drop has to take ownership of it. The drop method requires it to take ownership of self. So self is not passed into the drop method with a reference, it's owned. And when you own something and you don't give it back, that thing is effectively dropped. That's how drop is implemented. Then we got into the RC, and the RC is the reference counted type in Rust, and this allows us now to have multiple things point to something. And this is nice because we got into an area where we couldn't make a type that was recursive and unsized, right? Because Rust doesn't know how big it is, so it had to have a definite size. When we get into the world of RC, we're saying effectively circumvent that, and we want to circumvent that by keeping a reference count to that. So now Rust doesn't know in compile time when it should free something up with something like a drop trait. It instead requires something to call that drop for you. And the RC works by checking that strong count. So there's a strong count in the RC type, and every time you want to reference to something, Rust will increment that count. And then when that count gets to 0, Rust will then drop that underlying type. So the reference counted component allows us to do things like share data. And here's an example of that. We have this A, which is a list of 5, 10, and then B, which is a list of 3, and then A, and C, which is a list of 4, and then A. And in this case, the first element of A, that both B and C are referencing, this one would have a strong ref count of 2. And we talked about the idea that we can do the strong ref counting is really cool because now we have this component of being able to share data, right? But we can't mutate that data. So there's an additional thing that we can wrap now called ref cell, which allows interior mutability. And ref cell has some drawbacks on that interior mutability. Like one of them is that the type can't be shared across threads, right? We're going to cover some more of that today, but ref cell as a type has an API to it that you provide, and Rust checks that when you run it, right? When you're using that type. So that type, ref cell, has limitations, and we'll cover some of those today. And one of those limitations is, just like the types that the compiler checks for you, when you use ref cell, you can either have one mutable copy out or an infinite amount of immutable copies. Ref cell keeps that counter internally. It checks that. It says, do I have one copy out that is mutable, or do I have an infinite amount, up to an infinite amount of immutable copies? And that is checked at a cost during runtime, whenever you use those operations. So it follows the same ownership semantics that Rust follows. And I think we also talked about this, that this is kind of the theme. The theme is that Rust has the ability to check all of this stuff in compile time, and then it has taken these ideas and built these things that don't have checks in compile time that allow you to have these checks in runtime. So the idea here is that if you have enough of your constraints of your program to be checked in compile time, Rust will do that for you implicitly. And if you don't have enough information to do it when you're compiling your program, such as you're going out to the internet to create types on your list or something of that sort, then Rust still values those axioms. One copy that's mutable or an infinite amount of references that are immutable, then Rust has types that will check those not in compile time but in runtime, right? So you're paying a runtime cost for this, but you're getting the same memory safeness. It's guaranteed. And this is better than other languages like Go, to shit on the new language, which don't have this. So, like Go has the ability to push onto an array, and that requires the array to be mutable, but it doesn't check that this array push is only used in one thread. So if you have a simple array in Go and you share it with multiple, I think they call them Go routines or Go threads, the equivalent, whatever it is. I don't write Go, but I've seen this exploited. There's a really good talk on this too, just this one thing. But you share that same array with different Go threads, and they all push to it. You have effectively a memory problem, right? So Go doesn't protect you against that. It effectively says our types are not safe for our own Go threads. Upside, far simpler. Downside, far more risky. Okay, so we wanted to cover, I want to make sure that I don't summarize the one we're trying to cover here. We are trying to cover, okay, so we're 15.6 is the one we want to cover. Okay, let me summarize this one then too. So we went over the ref cell being a way out.
By the way, not to interrupt you, but
Yeah.
have you, I did write up the question on Stack Overflow.
He did, and I looked at that. Yes, it was good. The answer was good. So the answer to that was that the ownership semantics of the language are different than the memory freeing semantics of the language. The cleaning up always happens after the function is called. Whether or not that piece is owned at that point is a different question. So we got into the part of the book where we're talking about when something isn't owned, it can be cleaned up. That is not necessarily true. It has to be cleaned up after the function stack is done, if it's on the stack. So the cleanup always happens when the function call is over, even if there's no owner. It's not like, okay, there's no owner, therefore you're safe to clean it up. I still question how thorough that answer is, because you get down to these areas where you get an answer that's like 80-20, it covers 80% of the cases and not 20% of the cases. And you wonder whether or not like Rust running under sufficient optimization would just realize that, you know, it doesn't matter and replace that memory elsewhere. But that's what was given. All right. Yeah, and then effectively they're just taking this conjunction of reference counting and interior mutability, right, to make a list which you can share elements on and mutate the elements. And why is it important to mutate the elements in a list? Because you want the ability to extend the list, to push and pop, right? So if you're going to be able to push onto the end of a list and pop onto the end of the list, you need to make sure that your list has interior mutability, right? And that's how we do it. So here we're creating a list that has nil, or it has this cons of a reference counted ref cell of I32s and a reference counted list. This makes the list infinitely shareable, and it provides us interior mutability over every element in the list. Okay, and now we're on this page. Okay, so now we've done this thing, and we get down to this whole entire memory leaking component. So if we have a list, and it is, we have, I wouldn't say it's a list, though it could be. You have effectively a memory structure that's circular, right, that doesn't have a beginning and end, where the head points to the tail, and you're effectively looping around. And this can be useful in a lot of different cases. There's some memory databases that do this. But regardless, the question is, how do you ever decide that that whole structure is free? If the head points to the tail, and the tail points to the next item, points to the next item, next item, next item, until you get to the end of it, then it points back to the head, everything is pointing to each other, how do you end up freeing it up? So 15.6 is about that, and effectively what Rust does is what all languages do that have reference counting, including Perl, is they introduce a notion of a weak reference count, right? So Perl also has this too. This is the ability to point to something and then have that thing that you're pointing to maybe not exist, right? But the pointer still works if it does exist. So what does that mean? That means if it doesn't exist at the time you try to dereference it, you get something back, either an exception or the equivalent of none, something like that. So that's how Rust does it. So Rust has a strong reference count and a weak reference count. And now I really feel like we went over this, because I remember I had a question, and I think the question may have come from Brian, and the question was, why do we have to have that be a number? Couldn't it just be true or false, you know? Did that question come up last time? I think someone was asking something like that, the counter on the list. Doesn't matter if it's a counter, could it just be true that it exists or false? I seem to recall something like that. But anyway.
Well, I think the question was, why is there a weak count? Like, why do we
Yeah, that was it. Yeah. So we covered that part of it. So we made some progress in 15.6 even if we didn't finish it. And I don't know that I had a reason for that. It was a good question in my opinion. So the question was effectively, we have to count the amount of strong pointers because we go up, right? And then when we get to the strong pointer, it goes up every time you use it. So let's say it's at 3. And then when you stop using it, you start to drop it down. So you like free something up. You can go from 3 to 2, 2 to 1, 1 to 0. And when it's 0, you know that that thing has to be freed. So for strong pointers, the fact that you have a count is required. But on a weak pointer, nothing happens when you're at 0. So why does a weak pointer have to have a counter behind it? That was the question. I don't remember who asked it.
I think it was Kai.
Was it? Okay. So it was a good question. I don't know the reason. Yeah. It was on my list of things to look up, and I didn't look it up, and now it's bothering me. Fuck. Yeah, I mean, what we could actually do is we could look at the source here. Let's click on this one. So this is the RC type, and we have this pointer, phantom, and alloc, and we're looking here for weak. So weak is done with downgrade. And here's downgrade. And downgrade calls increment weak. So this is actually what it's doing. And the question is, why does this matter? Why can't we just set this to true, that a weak reference exists?
For downgrade instead of upgrade? Or deck weak?
There is a deck weak. But they're only using it for, so they take a strong pointer and they have deck weak, which removes the strength of the pointer, but it doesn't decrement the function count. Yes, it does, right here. Fuck me. Oh, okay. That's interesting. So it says here that the weak reference count also matters for deallocation. So now I'm really confused. So let's take a look at this. RS STDRC.
Yeah, I look at it right now. It says it's a allocation that since a weak reference does not count towards ownership, it will not prevent the value stored in the allocation from being dropped, and weak itself makes no guarantees about the value still being present. Thus, it may return none when upgraded. It does prevent the allocation itself from being deallocated.
It does prevent the allocation itself from being deallocated.
It's right here. It's on the STDRC weak.
STD. That was a really good question. The STDRC, you said weak?
Yeah, weak. That one.
Okay. There's another good question for you on StackOverflow. What is the distinction between the allocation being dropped and the allocation being deallocated from the backing store?
Okay, I got you.
The allocation being dropped versus the allocation being deallocated from the backing store. Those are the words that they're using. So they use these words and they don't really define them.
I guess we don't know what
I actually think that that's probably the answer. I think that the answer probably involves that, but goes a lot deeper. So like if you probably use something like glibc, it can free up the memory of the operating system. If you have that option enabled, and rather than just it saying this is still in the memory footprint for the program to reallocate in the space, it can free it back up to the operating system. That's my speculation, right? You get that? So a program has two different notions of memory. When you allocate memory to a program, generally the program keeps that memory for the entire runtime of the program. For instance, Perl will never give back memory to the operating system. It doesn't do that. It takes memory, and if you free something from that memory, then Perl effectively has retained the right to put new things there. But Perl doesn't go through the problems of saying you can take back this memory to the operator. In some areas it actually does, but in like the op tree it doesn't.
I guess what they mean is that even though the allocated, like whatever was there is not what was before, I guess the allocation itself meaning like the ownership by the program. So it's not gonna become a leak because it's still like part of the program or something like that.
But if a value is dropped from the allocation, what does that mean compared to the value being deallocated?
Well, it says prevent the allocation itself. I think what they mean by the allocation itself is like by deallocated meaning you free the memory so that other programs can use it.
Right, that was my assumption.
I think otherwise, allocation from being dropped is more like using a free call, and allocation itself from being deallocated is just keeping it in the, yeah.
But as far as I know, whether or not free, this is why I'm saying I think it's confusing. Whether or not free gives the memory back up to the operating system, like glibc is free, gives it to the operating system or not, depends only on the compilation of glibc. I don't think you have any other control about it. So for instance, Perl doesn't use free from glibc. It has pfree. The same thing of like Postgres, it has it.
Mostly user space.
SQLite.
Yeah, they have their own implementations of memory management outside of getting memory from glibc. So my question would be, if you, and they do that by they like allocate an arena, and then inside of that arena they play around with the memory, they have their own memory manager, and the free from glibc is not called. My question would be, if you're using glibc, then what is the distinction between these two? Because I don't think you can call glibc and say free it back to the program and not the operating system. You know, like that's, here's how you find this stuff out. On Linux you just simply say man free, man 2 free, man 3 free. Eventually we'll find the right one. There we go, man 3 free. And so there's free right here, and it only takes a void, it only takes a pointer, right? So when you call free, the free function frees the memory space pointed to by pointer, which must be returned by a previous call to malloc or related functions. Otherwise, or if pointer has already been freed, undefined behavior occurs. If pointer is null, no operation is performed. So let's see here, glibc free to operating system. In general, free doesn't lower the program break, but instead adds the block of memory to a list of free blocks that are recycled by future calls to malloc. This is done for several reasons. The block of memory being freed is typically somewhere in the middle of the heap rather than at the end, so lowering the program break is not possible. It minimizes the number of SPRK calls the program must perform. In many cases, lowering the break would not help programs that allocate Okay, anyway, complexity. I'll have to read that. I don't know. We'll save that for a different time, though. Probably thought it was a good question last time and didn't know the answer to it, and then it just bothered me when I thought of it again. But yes, that's a good question. So this concept of week allows us to effectively pull out a reference, and then we don't know until we use that reference whether or not it exists, right? So when we have a weak reference, when we want to later use that, we ask it and say, does the thing behind you exist? And it doesn't have to return that. And all of that is documented in this stdrc week. So you can see an example of that here. We have to upgrade the weak reference to a strong reference, and then we can see whether or not it is none, right? So if that strong reference points to nothing, then we get none. Yeah. Yeah, so here, when we call upgrade, we return none if the inner value has since been dropped. So a weak reference in Rust gets upgraded to a strong reference, and when you try to upgrade it to a strong reference, you either get the strong reference back or you get none. It's returning the option of the RC. So it'll either give you something that's a strong reference or it'll give you none. Okay. What's up?
None if it's already garbage collected.
Not necessarily garbage collected, because that distinction they just made, right? None if it's dropped. We don't know if it's garbage collected. That's my assumption there. Or freed, we should say.
So drop just means it's freed in the arena. Quote freed.
Something like that, yeah. Preventing reference cycles, turning an RCT into a weak T. Okay. Yeah, this is just what we said. There's nothing new there. Creating a tree data structure, a node with child nodes. So here we have a tree. Rather than doing a list now, we're making things more complex. We have children. So a node has one value and then children. And the difference is that children is a vector. So we have a ref cell, something that's interiorly, that can be muted on the interior. And that contains a vector, which is one or more reference counted nodes. It's also interesting that in this situation, this ref cell vec RC node, this is the opposite of what you normally see. You normally see RC ref cell, right? RC ref cell means you have a shared thing that has interior mutability. Now we have a vector, which is something that can be mutated on the interior, and it contains reference counted nodes. 1 or 0 or more reference counted nodes inside. So that's what we're defining the children as.
I never knew these children also watch Chinese Cocomelon.
I get the feeling that we did all this stuff, but anyway. So, is any of this new to someone? Does anyone have any questions on this? If not, I think I'm going to just try to fly through it. Here we're creating two different, we're creating a leaf and a branch. A branch in tree terminology contains either, sometimes they don't contain values. Sometimes you only have values on the leaves. But a branch is the point in which you hit define your leaves. So normally, when you erect a tree, you have these multiple different things that are called branches, right? And these branches usually don't have, they sometimes have values. This one does have a value. But you end up recursing into this and you find leaves inside of it. So normally these trees are ordered. So if you have a branch at the top, your root is like 10, then you would look to the leftmost element for something smaller than 10 and the rightmost element for something larger than 10, right? And you normally only have 2 elements. You don't have more than 2. In this one you do, and in many databases you do actually. So in databases you want all of your branches to contain the amount of leafs as one page read. So they're optimized from reading from the hard disk. So a hard disk has a certain set. Every time you go to read from it, you have to read a certain amount of data, and they optimize the tree for reads from the disk. So here we have no specifications on how many children we can have. So we could have 30 different children on that one branch. And then the question is, after you find the right branch, right, how do you know which leaf has got the thing you're looking for? You probably have to read every one of them, unless they're sorted, right? And we don't go into that, so. Adding a reference from the child to the parent. Normally you go from the top of the tree down. You don't go from the bottom of the tree up. But here they're showing you how to find the references from the child to the parent. And how are we doing that? Well, every different node inside of that tree now has a reference to the parent, right? So the parent there has this ref cell week. And why is it a week? It's a weak one, so the parent isn't kept alive by the children. So if a parent has 10 different children, but it has no branches pointing to it, then that parent can disappear. So think about this. You have a tree. Does anyone here not know what a tree is in computer programming? Is that a new term for anyone? Okay, let me pull up a picture of a tree, just so we're all talking about the same thing here. There we go. Actually, the other one is even better. This is closer to what we have. This is a bee tree. Okay. So the only thing that sucks about this one is that the nodes are also branches. That's not the one we have. Oy. Let's do this one, and we'll just keep it like this for now. Okay. So 4 at the top would be said to be, 2, 6, and 4 would be branches in our scheme. They all have pointers, references to their children. The children's are 1, 3, 5, and 7. So what we want here is 2 and 6 to not be kept alive by their children. That means that if you have 10 different children, you can still get rid of 2. How would you want to get rid of 2? Well, what if 4 isn't pointing to 2 anymore? If 4 isn't pointing to 2, you may say, now that 2 is not reachable, I want to drop it with all of its children, right? So if you want that semantic of saying, if the tree, that part of the tree is no longer reachable, drop it with all of its children, you may make this link to this weak. Now this will not stay alive because of this. Why will it stay alive? It'll stay alive because of the strong reference. So the strong references are pointing down in this case. The weak references are pointing up. So this to this, weak. 2 to 4, strong. Right? And if you think about it a different way, you could say, think about 4, 2, and 6 being of a different type than 1, 3, 5, and 7. That's why I like this tree. There's a distinction that's easy to make. Branches are 4, 2, and 6, and the leaves are 1, 3, 5, and 7. Right? So you can say that a leaf is a branch that has no children. All right. So, yeah, here's another way to think about it. A node will be able to refer to its parent node, right? If we go back to that graph, the node can refer to the parent node. 1 and 3 can refer to 2, but they do not own 2, right? And what is the semantic of ownership in Rust? It's about saying when this thing is responsible for being dropped. 2 can be dropped when 4, which owns it, is no longer needing it, loses that reference. But 1 and 3 don't own 2, so they're not responsible or take part in that dropping responsibility. All right.
But they drop with it, right?
They drop with it, yeah. Yep. And why do they drop with it? They drop with it because the leaf effectively doesn't sit independent of the branch that owns it. So the leaf is only ever accessible with that scheme, right? It has a parent and a child, right? That's the leaf. And it is only accessible in the branch, right? Why is it only accessible in the branch? Because right here, we say the children for the branch are ref cell new, and then we have this RC clone leaf, which is the leaf up there, right? So because of that, this RC clone leaf, this is going to be what is establishing the ownership semantics of that leaf. Now, here's the exception. The exception to that is this leaf in the branch notion that we have here is using RC, right? It's saying RC clone. What does that tell you? It tells you that the branch is using a reference count to get to the leaf. So you can have multiple branches own the same leaf. So to be more specific about it, in this example, 1, 3, 5, and 7 are all different leaves, and they're all owned by one branch. But in our actual code, we have stated that the branches themselves don't own the leaf independently. They own a reference count to that leaf. So you can have the same leaf in our scheme owned by 2 branches. You could have 3 here and 3 here. In which case, simply dropping the branch would not drop the leaf. Because there could be multiple places that it's owned, yeah.
You would have to drop all the references on
And then it would automatically drop. That's exactly right. I just wanted to say that because it is, the children here is not actually as simple as it normally is. Normally, you don't have this. Normally, you have a sorted tree, and your branches own their leaves, and they're only accessible in one way. There are cases where this is different, right? Like, let's say that the leaf is a piece of data on a hard drive, and let's say that the tree is an index. You can have the same piece of data on the hard drive indexed in multiple different ways.
It's more like a graph, right?
Well, a tree is a type of graph, right? So, but you could have that piece of data referenced by multiple different indexes at the same time. And if you wanted to do that, you want to index on both first name and last name, then the first name tree and the last name tree may have the same thing. Okay. So now we're at the visualizing changes to the strong count and the weak count. Okay, so now what we're going to do is they're showing you that when they create this leaf, they give it an arbitrary value of 3, and they create it just as the ones we've been talking about thus far. And now they have this println here on this, right? And they show here that the leaf has a strong count and a weak count. They get those counts by using these associate functions in RC. So RC provides these associate functions that take that reference counted type, and they allow you to get out of it the strong count and the weak count, right? Now, it's certainly not the only way to do it. They could have implemented it as a method, but they do it like this, probably because they don't want to show this internal stuff as, public facing, right? So they just say, we're not going to provide that as a method. But RC weak count, and they take a reference to a leaf, that'll work. And yeah, I mean, another thing you could do here is implement this as display, so you saw this every time. But they've just said they wanted to print it out. Okay, now they're doing this component here where the branch, the leaf's parent, is going to store a copy of this branch. Yeah, okay. I hope I answered the parts of this that I thought were relevant. I really think a lot of this is not all that relevant for you, because creating these data structures is useful, especially if you're going on like a gotcha interview and you have these interview questions where they want you to do something like that, create a linked list that can be traversed in the front to the back and the back to the front. Knowing this kind of stuff is very useful for that, but it's not all that useful for doing business work because generally speaking, you're using someone else's library that already does this for you. All of this stuff is built on top of unsafe cell. Unsafe cell effectively allows you to write code that is safe by checking it in runtime. And because of that, there's a lot of different things that come after it. There's mutexes, refcell, RC, cell, all this other kind of stuff. And you don't have to learn how to use all of it or any of it most of the time because other people are doing it for you. All right. So now we're in fearless concurrency. Okay. We have an hour and a half, which is good. Okay, I like this chapter a lot, and one of the reasons why I like it a lot is because we've done a lot of work to do very simple things, and now we're going to do very complex things with very little work. So this is the area where Rust really starts to totally kick ass, right? You've seen a lot of Rust complexity doing things that are very simple that you would do with ease in other languages, right? Now you're going to see things that are extremely complex in other languages that Rust does with ease. So this is really the area where the handoff is total and complete, And generally when you have more people in the class, it's kind of fun. You get to say, how many of you have ever written a multi-threaded program? Most people don't have their hands up, And it's not because they've never needed it. It's because it's so damn complex. It's difficult to get right. It's a very skilled thing. Hands go down here, And this is an area where if you were to pick up Rust, it would be natural and very easy for you to do it. You'd have a lot of options, and they would all be very easy for you to implement. But here's the crux of it.
Major function in Postgres and just add it up as a connection. And your connection have Postgres to other threaded code.
Well, Postgres isn't multi-threaded. I mean, it has very horrible multi-threading. It does have a concept of multi-threading, but it's not something you want to write home about. So.
That's what I do with SQLite. I just write my function and call it in SQLite.
This will be many times faster than that, So let's go ahead and hit on this. This has got some concepts in there. The two main concepts are concurrency and parallelism. And here's how it kind of breaks down. Parallelism means that two different things are working almost always to compute the end result together, harmoniously, right? That's what it means to have something run in parallel. And because the definition of parallelism is so strict to that, two things working together to make an end result, it is almost entirely something that is mathy in orientation, not something businessy in orientation. So things that may be parallel would be something like crawling one of these trees. There are methods in which if your tree is sorted, let's go here, let me show you something here. Let's look at a merge sort. What's up?
Shaders as well.
Shaders are very mathy, right? That's one of the more mathy, because then you're talking about like matrix operations and that kind of stuff. Okay. Here we go. Just ignore that it says in Java, and we're going to take a look at this. I like this, a merge sort example to me is a very clean method of demonstrating parallelism. So let's say that we take a list, right? 15, 13, 43, and 10, and we want to find one of the fastest ways of sorting that list. Now, this is not the fastest way of sorting the list. This is the most mathematically pure way of sorting the list, right? This makes the mathematicians happy. And for a long time, it was assumed if we could just make this quick enough, everything would be rosy. Turns out there's a lot faster ways to sort a list than this. But let's take a look at this one, 15, 13, 43, and 10. Now we know that that list has got 4 things, and we want to sort it. So what do? Split it in half, very easy. We split it in half, and we send to one thing that's computing the 53 and the 13. We send to the other thing that's computing the 43 and the 10. We tell both of them, sort these lists. What do? They split it, right? Now, what if they have more than 2 items? It makes a lot more sense to split it, but they don't. They have 1 item. So he splits his list, he gets 53 and 13, right? He says, now they're gonna send both of those lists off to another piece of computation, right? Another core. And they're gonna say, sort these items. And those cores are gonna do what? Split it, but they can't, because there's only 1 thing. So both of those cores are gonna say, there's nothing I can do here, I have 1 thing. That thing is a 53, the other thing is a 13. They're both gonna send it up and say, this is my list sorted. Now, that guy who just told the 53 and the 13, who just told these 2 cores to sort whatever he gave them, right? He's gonna get them back, and they're now gonna be sorted. They're gonna be in an order that's sorted, right? So now he's gonna say there, okay, your side of the list is sorted, my side of the list is sorted. Now I know yours and mine are sorted, I just have to add them, sort them together, right? So now he knows that his side is sorted, this side is sorted. There's only 1 element in this case. He just gotta say which one's bigger. The 53 is bigger, put it on the right. Now, if there were 2 elements, he'd climb through both of them in parallel. He'd say, okay, is the 13 bigger than this? If so, we'll take the 13 first. We'll take the 13 second. The other one, the smaller one, goes to the other side. And he'd just keep doing that. He would recurse through it. He only ever has to look at 1 element at the time, right? Because those lists are already sorted. So he's only ever looking at 1 element and saying which one's bigger and smaller. Okay, so he gets this list sorted, and then this guy gets this list sorted. He did the same process. And now again, the thing that sent them all there gets both of these lists back and sorted, and now he just has to assemble it. So what does he do? He says he's got 10 and 13. Which one's smaller, which one's bigger? 10 is smaller. He puts the 10 over here. Now he has 43 and 13. Which one's smaller? The 13 is smaller. Puts the 13 over here. Now he has 43 and 53. Which one's smaller? 43 is smaller. Puts the 43 over here. Then he has only 53 remaining. He puts it over here, and the list is sorted. But in doing this, you have maximum use of all of your computational resources, right? That's not to say it's the most efficient, but you have made that task extremely easy to parallelize. And that's called the merge sort. That's the ideal thing, right? So this is a case where you have a parallel operation. You can have a bunch of different compute units all working together to compute a task. Now, what does it mean to have concurrency? Concurrency usually means I/O is done at the same time. So this is something like, there's a lot of processes that are especially business oriented where you're waiting on something that isn't you, right? An example would be if you want to go to a website, pull down the data, and then you want to go to the database and store the data. That's an example. Now you have 2 things that aren't you. You have the website and the database. But why would you want to make the database wait when you're going to the website, or make the website wait when you're going to the database? You don't. Let's say you want to crawl all of Amazon. You want to talk to Amazon with 5 different lines of communication, pull down 5 different product listings. You want to insert them into the database. There's no synchronization there between the database and Amazon. You tell Amazon, hey, I need you to serve them faster because my database is waiting for me to call you quicker. Amazon's going to give you the finger. And if you tell the other side the same thing, your database is going to tell you I can't move faster, spend more money on my hardware, you know? So these things aren't going to work. So you're going to go to the Amazon 5 different times to pull out 5 different listings. And as those listings come through, you're going to have work to do. Because now you can say, I've got that down. I know what data I need, put it in the database, put it in the database. And however many times you want to contact the database and have that communication, something is going to have to do that ushering, you know, that's saying, okay, I can talk to Amazon another time, let me call them again. I can talk to the database another time, let me insert another row, right? This task is called concurrent because you're waiting on something else and you're trying to make the best use of your resources, right? So we differentiate between a task that is concurrent and a task that is parallel. And the primary reason why we do that is because some things, not Rust, some things are very good at doing tasks that are concurrent, and they suck at doing tasks that are parallel. So there's a need for that distinction, right? The amount of things that are very good at doing tasks that are concurrent are numerous at this point. Most good languages are very effective at doing things concurrently, especially if you're a senior level programmer. Perl, Python, Ruby, PHP, all of these languages can do, especially JavaScript, can do things that are concurrent and have high concurrent demand, right? JavaScript is extremely concurrent. That's one of the reasons why you have these things like promises and callbacks, you know? All of these help you do concurrent tasks very quick and efficiently. But JavaScript is not parallel. It sucks at this. Has minimum functionality for parallelism. Got these things called web workers, and they're dog shit. So if you want to do something like a merge sort over 10 billion element list, JavaScript is going to come to a screaming halt. It's going to say, I don't know how to use, you know, the 10,000 cores while I'm merge sorting this list or whatever. It's going to be very difficult for it, right? Because it's not good at doing all of those tasks at the same time, whereas Rust is very effective at it. So starting off the chapter, this distinction between concurrency and parallelism. Rust is very good at both of them. I will say this too, it is always easier to get concurrency done right and to write programs that are concurrent than it is to write programs that are parallel, right? So to write a program that is concurrent in Rust, we use this one framework called Tokio, and it'll solve all your problems. If you're coming from JavaScript and you say, why is it always easier to do things that I do in JavaScript than it is to do them in Rust? The answer is almost certainly because you haven't jumped on the Tokio bandwagon. In Rust, we do everything that requires concurrency with Tokio, unless you're a special snowflake. So it is the big 600-pound gorilla that handles all of our concurrent needs. If you want to do something like a web server in Rust, we use something called Axum. This is like the one that, I mean, I was an early adopter of Axum. I've been using it since day one, literally. But Axiom is now part of Tokio RS, and Tokio RS includes a whole slew of projects, right? So we have Axum, Tokio, Mio is the IO library that they use underneath. There's a testing tool for it, a tracing framework for it. There's pretty much everything you could want. There's another one called Request. This is also based on Tokio. But anyway, all of these different things use concurrency all through Tokio, and it's very easy to do them. Okay, so now let's talk about the primitives here that Rust has to make things parallel or concurrent. Both of them use the same primitives, right? Under the hood, they're both doing the same things. Rust uses this thing called thread spawn, and it's that easy. We just say threads : spawn, and we give it this anonymous function, or closure, however you want to frame it. We went through the distinctions earlier. I'm not going to go through them again. But the idea here is that thread spawn knows about whether or not it's safe based on what you're moving in, right? If it's taking ownership, it owns it. It can do whatever it wants. And it doesn't have to worry about other things shitting on that memory block because you've passed ownership in. If not, Rust has the ability to tell whether or not something is safe to be given to spawn based on whether or not it has this sync trait. So there are two traits that Rust uses. One of them is called send. It means that another thread can take ownership of this thing. The other thing that it has is called sync. It means that thing that is in a different thread can reference this data. So these two different traits that Rust has, by the way, the great thing about Rust, these two different traits are implemented by the core team. And because we all build on top of that, they automatically get carried forward in our own implementations. So if you have a struct and everything is send and sync inside of the struct is send and sync. It already happens for you. If you implement something that's not send and sync inside of the struct, then suddenly the struct is not send and sync, and this doesn't work. And when you try to use it like this, it'll say, struct is not send and sync. This is inside of it. What kind of things can you not put inside of a struct that make it send and sync? File handles. A file handle, the ability when you say, I want to open a file, and Rust says, here's a handle, and you say, okay, I want to write to this file using this handle, send this data to this file. That is a method to communicate with your file system. You can't send that magically to another thread. You know, what's up? Sure, you know, there's a lot of things, you know. I'm not going to go through all of them, but there's a lot of things that are like this. I'm just giving you an example. Most data, numbers, strings, all that kind of stuff is send, right? Most references, I don't know if I can say that. Many references are sync, and some of them are one or the other. And you don't have to remember any of this shit, by the way. That's another great thing about Rust. It's cool to know it, but when you fuck it up, Rust comes back and it tells you. So don't get overwhelmed. You don't have to know it. I don't remember what is send and what is sync. And I think most things that implement send mean the reference to that thing implements sync. But not all things. There are certain things that are not that way. And I know this because I've asked this question. So if I come down here and go like Stack Overflow, like I said, I live a very public life when I'm learning shit. So it's nice when I make a mistake, or when I have something I don't know, I can quickly find it out. So if I just click on my name here, it says user up there with me, and I can just say send sync. And here, yeah. Is the sync trait a strict subset of the send trait? What implements sync without send? So in which case is there, and this is an actual, I was reading a book. I was reading a programming Rust book that I recommend to all you suckers. And I found this thing in there that does it. And it turned out that it was an error, right? So I was actually just asking someone a question, because they had this part here, they have this big gray circle they say is sync, send, and the white circle they say is sync, and they show things that are outside, like RC string and this, and I forget what they said about them, but I had a question on it, and it turned out that someone else said that the wording was shit. Yeah, here's the author. Yeah, this is wrong, my mistake. We'll have a fix in the next edition of the book. Thanks for asking about this, and thanks to Alice and April and Applet123 for answering. So the actual author of the book answered the question on Stack Overflow and said that it was a mistake in the book. Anyway.
In Node.js, there's no async equivalent for detecting if the file is. There's only a sync version.
Yeah, well, there's a lot of things too that can be made async, but they're actually slower and they provide no benefit. So making something synchronous is sometimes faster than just assuming you can make it faster being asynchronous, right? Like sometimes you just add overhead to a task. It's a whole nother thing, but that's why that exists. But here you have this kind of stuff where it is so complex and so niche, the author in the second edition of the book made the mistake, right? And I'm telling you that because it doesn't, the compiler will bitch when you try to do this kind of thing. You know, it'll say you need to go back and check yourself. Anyway. Okay. So with Rust, we just call thread spawn, and we can spawn the thread. Here we're spawning one thread, and we say for I in 1.10, and then we tell the thread to sleep, right? So the thread goes to sleep. A thread is a unit of execution, but unlike other units of execution, like functions, a thread is effectively a unit of execution that your kernel can put somewhere else. That's what a thread is. It is the smallest unit of execution that your kernel can put somewhere else. A bigger unit of execution that your kernel can put somewhere else is a process. So these different sized execution units, right? Things that your kernel can schedule and decide, I want to put that on a different core. I want to give that a different cache on the CPU. All those types of things are there, right? So in order to get one of those units of execution that your kernel can schedule, we just say threads : spawn, and it spawns this new thing called a thread. And a thread is like a process, but it doesn't have any of these unique identifiers or access to your file handles or any other kind of shit. So the deal here is that we have one of them, and it's effectively doing this iterating 1 through 10 and sleeping for 1 millisecond. And then down here we say for I in 1 to 5, so we're doing this 5 times. We're saying thread : sleep, and we're sleeping again for this duration of 1 millisecond. And then down here, we're seeing what it printed out, right? So we get the main, the spawn, the main, the spawn, the main, the spawn, the main, and then 2 spawned. And here's the other thing here. Yeah, let's look at number 4 here, these two. This is the key here. From the spawn thread. Both of those kick off at the same time, or come at the end. And the point here that they're trying to make is that these threads operate independently, so they can key off in different patterns, right? They're independent of each other. So when you shrink down that duration to 1 millisecond, or better yet, have no milliseconds between them, right? you may schedule one of those threads on a faster core. It may get done quicker, right? There may be 2 things executing on one core and 0 things executing on another core. The one that has 2 things executing on that core is going to have interruptions, because a core means it's 1 unit of execution in the silicon. The CPU can only execute 1 thing in the core. So if the core is executing 2 things as fast as it can on one core, they're going to have to share it. And if the other core has nothing executing on it, then the thing you schedule to it can take the entire core. Now, I'll tell you this, things are even more complex than this. Why? How many people have a new Intel chip? Anyone here have a new Intel they bought in the past 2 years, 3 years? You know, you see them, they schedule them now with P cores and E cores. Okay, that means that you have 2 different types of cores on the same chip, not just a different amount of cores. So previously, Intel was unique in saying that we don't ever want to do that design, it just complicates things. Then everyone else went to that design, and Intel got their asses smoked. And then Intel came back and said, that was a really good idea, we need to do that too. That's kind of how Intel works, you know. So the E cores are efficiency cores. Those are cores that take less power and they're cheaper to make. The P cores are performance cores. Those are cores that gamers want. Now, does that mean that an E core has no value? An E core has a tremendous amount of value, right? Because it's still fucking fast. But to make a P core means you got to get everything right in that silicon. So generally what Intel does is when they make a core on a chip, right? They do these with these things called chiplets, and there's a high failure rate on these, right? They probably have 10% success on it. 90% of them are trash, right? So they have to make the decision, what are they going to do with them? Well, one of the ways that they've advanced is they say, rather than just throwing them all out and saying we're only going to put the best core on the chip, let's put those cores down as disabled in some fashion and sell them to you as an E core. And so very frequently the E core comes from like a bad run or whatever of the P core, you know? But all of that to say, they take less power and they can still execute stuff. And when you don't need that power, like for instance, instant messaging or running Electron apps or doing that kind of slow shit that doesn't make a difference, your kernel can actually schedule that task onto the E cores. Now actually this is probably one of the failures of Linux. I don't think it has that ability yet, but Windows does. We'll just ignore that. I don't think Linux yet has the ability to be P core or E core aware. But all that to say, the different number of cores all execute shit at the same time, and that doesn't mean they execute things at the same speed on each core. So things come in at different rates. And that's what I think we're going to see here, if they're not already trying to show it. So one of the other things to say is that when we did this up here, let's go here. Oh, okay. This is actually what they're trying to show you. See, I should actually read the text rather than just reading the code. But I'm not going to change. Look at the top. We say 4i and 1.10, right? The highest number there is 10. That means somewhere we should see 10. But if we scroll down, you see these numbers here, we don't ever see 10. Why don't we ever see 10? Does anyone read it and know?
Is that because the dot dot is exclusive, so it doesn't
No.
include the last number?
Go back to the code.
Oh, it's because of the.
Does the main thread stopping has anything to do with the spawn thread stopping as well?
That's it, Brian got it right. So you're not exactly right, but you're close enough, I'll round up. The problem is, these threads that you're spawning, the thread you spawn that's counting to 10, right? There is no guarantee that the main thread will live long enough for that thread. So if the main thread dies, it's gone, the file handle is gone, and the thread that you've just spawned is no longer able to print anything. Everything is cleaned up, the process is over. Your thread, on the other hand, hasn't finished. But you didn't tell your program you want that thread to finish. So in this program, you have 2 threads. You have the main thread, which is everything that's not thread spawn, and then the thread you spawn, which is just the shit inside of it. And the thing that you spawned is taking 10 milliseconds to finish its execution run. But the main thread is done in 5 milliseconds. So the duration of the time between the 5 milliseconds for the main thread and the 10 milliseconds for the spawn thread is unaccounted for. And when the main thread is done, It's not waiting by default. Enter the next section. How do we make it wait? Now here's something I would argue. The default behavior is horrible on this. And it's not Rust's fault. Everything does this. I don't know what idiot said it's a good idea to make it by default, let the main thread outlive the children threads. I think it would have been a much better user interface for the main thread to have something like force exit. You call that when you don't want to wait for the children. And then make the default behavior to wait for the children. That would make a lot more sense to me. But instead what we have is this thing here called handle join unwrap. And handle join says you want to join all the threads together. So all of these threads that are discrete, that aren't necessarily joined with the main thread, get joined. And now, effectively, your main thread will block and wait for them all to finish. Now, what if one of them doesn't finish? Well, now your main thread will never finish either. So you got to pick your poison on that, and that's the poison with this one. But this is always what you want. I don't think I have ever once written a program where I said, I don't care if my main thread finishes first. You know, my children thread,
Well, I guess if
don't wait.
the thread is waiting on a response and you close the program, you don't care if you didn't get it back.
When would that ever be the case?
Well, I'm thinking about it from a web dev perspective. Like, if you usually like a promise is just a listener waiting for the response, so you can do it as a thread, right? But if you close your program, you don't care anymore if you receive a response.
Suppose that will be an example of a case where you may not want to wait for your children's thread. Yeah.
Example would be making a bunch of concurrent WebSocket requests, and then but you don't want to wait for the WebSocket to close when you're done. You just close your program and
That's what he's saying. Because the user says they want to close their program. Conceptually, when a user wants to close their program like that, they want to force kill their program. I think call force exit when the user sends a signal they want to close their program. So send something like a sig-die handler that force quits their program. But you're right. In this case, you don't care about anything else except cleaning up the program, closing the program.
right, I always want to wait.
Yeah, I always want to wait. He always wants to wait. I'm telling you, I've never not done this. I've never not handled a join. You've given me a case where I think that would be the case. That's very slim, but good job thinking of that on your feet, you know?
Maybe because on the web dev side of things, you care a lot more about responsiveness. So many times you throw things to happen when they're done.
But you also care about failing fast, right?
Yeah, but it's awkward to say, like the only case that this could be true, which is why I congratulate you for thinking of this on your feet, is when the user actually says, even though something is going on, I want to exit this program now, right? That is the user being more random than uranium. If the user did something to begin with, like sent out 10 different requests, why would they do that if they don't want those requests back? I'm not saying it's impossible, but generally speaking, I would expect the user that wants to close their program now to not shoot off 10 different requests. Like if they say they want to go to google.com, they go to google.com, why would they want to close their browser before they got the answer back? You're right, it could happen, but generally speaking, I think most users that say they want to go to google.com want to go to google.com for a reason, not because they want to close their browser in 3 milliseconds, you know?
I guess like if you're on a browser and you open, usually browsers nowadays like it's component based, so things load when they're ready. So maybe you're waiting for one thing to be ready, then you click on it, you move to a different site. All the other things that were loading, you don't care about them.
Yeah, but you wouldn't want to abandon those threads. You could still say in your main program, you know, wait for all of the threads that you've used to come back to me. You don't have to leave them stranded,
Think
you know?
about, let's say you're on a program and you have a specific view. And in this view, you have asynchronous operations that compute things and then they show on the dashboard. And then you click on a button to go to a different view. Now you don't care about the results of those things.
But I'm saying the only time that would matter is if you were closing the program. If you're going to a different view, unless you're relaunching the main thread, it doesn't matter. When you have a main thread, the main thread is the browser. The browser telling it that I want to wait for all of my children threads to come back before I let you close is fundamentally different from saying, I don't care what those results are, I want to do something else. You know, so the X is the only case that, you know, you hit the X, you say, I want to go now, You know, I don't want to wait for these to come back. Okay, you know, that's the exception. You're done. I can't think of anything else, you know? And it's only the exception because it's not rational. You're telling me a human wants to close the program after they just told it what to do. Yes, if you're that, you know, humans are stupid like that, but there's no other case that makes sense to me, you know? Anyway, I'll only say this. I always join my handles at the end. I don't ever not.
So when you unwrap, does that give you like an optional result from the anonymous function return or something? Like could you return something from that function and receive it when you unwrap it?
I think it gives you back the result of all of the functions that are called. But it may also give you back whether or not there's an error from the join. That's a good question, so let's figure that out. So let's look here, rs join.
Because like handle is linked to a single spawn, right? As far as I can see.
Here, this is what you're asking. What happens when the join handle, right? A join handle detaches the associated thread when it's dropped, which means that there is no longer any handle in the thread and no way to join it. No, the join handle does not contain the result of the thread. I don't think anyway. There's no demonstration here where the join handle has if the associated thread panics, error is returned and the parameter is given to panic. So the join handle seems to return the result, and it looks to me like the result is let me check this out one more time here. Spawn. Nope, it returns the result. Okay, it either returns the result or it returns an error in the event it panics. So let's say that you spawn off into the thread and that thread panics, something in it calls unwrap and it dies. You're gonna get an error back, and when you try to unwrap it, you're gonna die, right? Or you'll get the result back, as they're doing right here. So they're saying result is computation.join unwrap, and then because result is presumed successful, or it's going to die, you can print out the result. So yes. But in very many cases, I have said I don't care what the result is inside of the thread I'm spawning. I need the thread to do something, but I don't care whether or not it finishes. Or it succeeds. I don't care whether or not it succeeds. I want it to do something, I don't care whether or not it succeeds. I just never say, I don't care whether or not it finishes. I always want it to finish. I don't care whether or not it gives me back success. You know, that's much more common. Okay. Okay, so now here's the example where it's printing out of order, right? This is always something that you go over when you're threading, because you have to press this a billion times before people wrap their head around it. Your computer can execute multiple tasks at the same time, and the only way to see that is with threads that are running at the same time. So you show them that with threads, now all of these threads are executing concurrently, in parallel, either. Let handle equals thread spawn. In this case, we have this thread handle, and we're joining it now. And because we're joining it, we get to the bottom, right? So 1, 2, 3, 4, and we're done. So notice where the handle join is here. The handle join is here in the middle of the program. You can put the join wherever you want. You almost always want it the last thing in main, right? That's almost always where you want to put it. Here, I don't think this makes any sense except for demonstration. It may make sense if you want to join and get the results, like Brian was just talking about. Then it may make sense not to have it as the last line. But you're going to want to, at some point, make sure you have let all of the threads you've spawned finish, even if not with success. Yeah,
So this join is a blocking operation then?
yes. And it only blocks if the threads have not finished before you, which sometimes never happens. You should always handle it, right? But very frequently, I will write a program where I know that to never happen. That's why it's easy to forget about this. And then you have an error, like the server gets held up on a keep alive or something like that in communication over HTTP, and now you have a real problem, you know? So like sometimes you'll say something like, I want this to retry 4 times, 5 times. I'm making a JSON request. I posted that I want to create a new user. And in the normal course, my thing that I'm posting this JSON request for will retry if it fails 4 or 5 times. I could spin that off to a thread and say, go create my account, right? I could assume that that works and it always finishes before my program. And then one time, their server turns off when it hits it, you know? And now my thing hasn't waited its 5 retries. And the program's done. Now in this type of case, you've hit one situation, which because of their server, your program is no longer finishing on time. You know? So sometimes you hit these areas where what should only be theoretical ends up becoming a real problem. And that's where it's really easy to say, oh, I fucking forgot to join these threads, you know? And you know, that could be a very hard bug to find, because now you're debugging your program, you're saying, this program's worked for the past 6 years, why doesn't it work? And it always created the accounts for you. Now it's hitting the same endpoint, it's still trying to create the accounts for you. But what you don't realize is you haven't waited long enough for that server. It's running slow today or something, you know? And your main thread is finished first.
Can you create a thread within a thread?
Can you create a thread? Of course, yeah. And you very frequently do that. And in fact, CUDA is all about that.
Because then you could join within the thread, so that you're parallelly waiting for it without blocking.
Isn't that what merge sort is?
Yeah, that's what merge sort is. Yes, the way I recall this working, a thread that joins waits for all of its children threads, and it goes all the way down the thread tree. So if your thread joins, you wait for not just all of your children's threads, but all the threads that they spawn too. But that may be something to look up and try. The point is, you don't ever have to worry about these crazy ass cases if you always join. If you don't always join, you got to worry about that crazy ass case. I don't know what the right answer is there. I'm making assumptions. I'm speaking out of my ass. I assume.
Because I'm trying to relate it to like an asynchronous function. So like if you're waiting on an HTTP response, you might still care about the answer, but you don't want your main thread to stop. So you join that.
In practice, what you do is you always have a timeout, which is 30 seconds or 60 seconds. And if it times out, then you just crash the whole program and rerun the whole program as a new process.
Yeah, but you don't want your program to stop doing everything.
You do. If the HTTP request times out, you just simply, it's cheaper to simply start over than try to reconstruct the state afterwards. I'm telling you, from practice, it's easier to simply just redo the whole thing when it times out.
I was thinking more
And
you set the timeout enough so that more than 90% of the time it won't happen.
It just depends on what you're doing. I'm not going to make a statement there that you don't want to recover from a crashed thread or a thread that times out. You very frequently do. But oftentimes you get down to an area when you're talking about threading and concurrency, the question is, what are you really trying to gain? When it comes to a merge sort, if you're sorting a list that's got 200 billion elements in it, and that's the main function of your program, then you're writing that parallel task to achieve performance in your lifetime. You know? Otherwise, it wouldn't be doable or something of that sort. Whereas if you're talking about correcting from an incident that happens once every 5 years where their server doesn't work, it may just be easier not to worry about it, to crash the program and rerun it. You know, so all of these types of considerations have to be taken into account. You know, what are you trying to achieve? Generally, you try to achieve concurrency and parallelism when it is required. Now, the reality is, as programming goes on, it's more and more required. If you look at Perl off the shelf, you have 0 concurrency, 0 parallelism, nothing. No core library in Perl is parallel or has concurrency built into it. Perl doesn't have an event loop built into it. Python doesn't have an event loop built into it. Ruby doesn't have an event loop built into it. PHP, no event loop built into it. All of these languages are antiquated. That's why Node ate their lunch. Node came to the market and it said, you know, it's fucking 2005, everyone wants concurrency now. Why don't we build the event loop into the language? Now suddenly Node had a huge leg up over everything that came before it. Why? Because Node was the only one that off the shelf had concurrency, and it kicked ass. It had promises and it had callbacks, and with these two very simple mechanisms, you could write programs that were highly concurrent, not parallel, but highly concurrent. It looked a little different. You had these callback trees that got a little wavy at the beginning, you know, but it was very easily done, and it allowed you to outperform all of the languages that preceded it with very little in the way of added complexity, right? So it was a better compromise. And you know, to this day, if you want to do what you do in Node with Python, what do you use? You use Twisted. You know, if you want to do it with Perl, you use Mojo. All of these are different things that add on event loops to bring these languages, these older languages, up with Node. You know? Okay, well now you're talking about that's your bread and butter. You know, it's letting you get your job done. Do you have to handle an account creation that fails, or can you just restart your program? I don't know. But you implement these things as you need them, you know, is generally how you write successful software. And you don't worry about handling all of the potential exceptions from remote clients when you can otherwise just restart. So it really just depends on your use case. You know, not everything is mission critical. The vast majority of what programmers do isn't mission critical. And a real good question is whether or not preparing for things that are not mission critical is a bigger waste of time, you know, than just letting them fail. All right. Using move closures with threads. So now we have this concept of a thread, and the question is, how do we get data into a thread? What's up, Robert? How do we get data into the thread? We use this, this move thing here, and move allows the thread to take ownership of something. So here's an example of a thread that doesn't work, right? Why doesn't this work? Because we're saying thread spawn and we're giving it the vector, right? And it doesn't work because we try to drop that from outside. So how can we allow a thread to access code that the main thread is dropping? How do we know whether or not the thread that is accessing that vector is completed before the main thread tries to drop it? We don't. So the Rust semantics is that we have to give ownership to the thread we spawn. And how do we do that? We use this thread spawn move. Thread spawn move says this this continuation is this closure rather. This closure is using this vector, and in order for it to use it, we have to move it into this closure. We're closing over that vector, and in order to move it in, it has to take ownership. Now the thread that we're spawning has ownership of it. We can't call it from outside. The Rust semantics prevent us from doing that. So it's that same component we use in all other closures is the same functionality to make threading safe. And that's the advantage of Rust really, is that this language that we use to communicate in other parts of the language that suck when you're learning it, now they're a lifesaver, right? Because now you don't have to track what thread has what piece of data. The same thing that Rust bothered you about the first 15 classes we did with how closures have to own the data and how we have to use this move thing to get that data into the closure didn't necessarily make sense then. Now it makes total sense. You know, now you're used to seeing these types of errors from it. You got a question?
So it just knows by whether you're using it inside or not. So you just need to use it inside for it to move it.
Yes. It can take an argument too. Like you can have an argument here that it takes in is an argument that's passed into it, but thread spawn doesn't provide any arguments of the function. So thread spawn just uses move to say whatever I'm referencing from the outside scope, you can't just reference it and close over that. You have to take ownership of it, right? So a closure can close over a variable that it doesn't take ownership of. In this case, it has to take ownership of it, therefore move is required. All right. Yeah. See, so the Rust default action here for V is to borrow it, right? To borrow V. But move tells it it's actually okay to take ownership of it. And the reason why you can't borrow the vector is because it's in a thread. So you have to move things for the thread to have them. Later you will see things like sync, which is the method of referencing something from outside the thread. Some types provide sync, and if they provide sync, you don't have to move them in. Using message passing to transfer between threads. Okay, so message passing is a method of communicating between different threads, and there are different types of message passing primitives that Rust has. And those are all identified by P's and C's. P's always mean producer, and C's always mean consumer. The other thing that it has is S and M's. S always means single, and M always means many. So these SMPCs tell you whether or not you're a single producer, multiple consumer, multiple producer, multiple consumer. Sometimes you have multiple consumers, single producers, all of these types of things. And I don't remember which ones you have and don't have. I'll be totally honest with you. I just look it up. But I use them all the time. Single producer, multiple consumer, rather the opposite. Multiple producer, single consumer is the popular one. That is MPSC, right? And that's this one right here. There you go. That's the popular one. And what that means is, why is this popular? It's popular because if you have 10 different threads working, and each one of those threads wants to call Amazon one time, get the web page, and parse the web page, pulling out the listing name, the retail price, the comments, the rating. That's all work, right? It's work on two parts. One, I got to go to tell Amazon I want the page. Two, I got to parse that HTML to get the data out I want, right? You may want to open 10 different threads that are all working through a queue of Amazon listings doing this. Get me the data, parse the data. Now, all of these different threads that are pulling through this listing queue you've got, they're going to have to wait to communicate back to the main thread to say they're done. That's where MPSC comes in. They're all producing data for you, and you have one thing consuming that data. Why do you need multiple things producing the data for you? Because it's a lot more work both computationally and on I/O, the calls to Amazon. So you may want to scale that part in multiples of where you're at. So let's say you have, it's 3 times slower to parse the web page and talk to Amazon than it is to insert it into the database. You could say, I want to spin 3 threads, 3 worker threads up to handle that. So I'm going to use MPSC, spin off 3 threads, give each one of them ability to write back and send me that data. And it's very easy to do this. This is the joy of Rust, I think, you know. So you say function main, you say let txrx equals MSPC channel. Now I have TX as your, has anyone here been to TXRX labs? Hands up if you've seen it. God. You've been or you haven't?
Well, we have been to the place that used to be TXRX.
Okay, were you there when it was TXRX?
Not when it was. No. It's still a creative.
I've been by the one-off navigation. I've been outside of the one-off navigation.
What are they doing with it now?
I don't know.
That's interesting to me. I've never heard of anyone going there after it wasn't TXRX, but sure. Yeah, TXRX has been around to 3 different places. I was originally going to be one of their founding members. They wanted me to pay them, I want to say, $1,200 for that, right? Yes, it used to be very expensive. Now it's $50 a month or something, but it used to be, I want to say it was $1,200 to be a member there. But they started off in Caroline, in the museum district, and they moved to they had like 3 warehouses off in navigation. They used to have one warehouse that was for woodwork and one warehouse that was for metal shop. And then they got their 3rd warehouse at the end, and that was just for arts. And I actually thought I would like the Arts Warehouse the least, but I have gone on so many dates with the Art Warehouse. That is amazing. They do all kinds of really cool shit there. The women love it. They do like leather work and pottery and all kinds of stuff where you can like do with your hands and work on different types of things. It's cool. But if you go to TXRX on the website, you can see like what kind of events they have scheduled in their calendar, and they're not expensive. It's like $50 to go to a pottery class or something like that. And it's kind of neat if you've never done anything like that. It's totally off the, it's totally left field, right? No one does that. But if you're interested, go check it out. They also do like soldering classes. I always wanted to take the welding class, If anyone wants to do the welding class at TXRX, message me. It's on my list, it's on my bucket list, but I've only done the fucking feminine ass classes there, the pottery and glazing and that kind of shit. But I still like it. It's still amazing. What's up?
Probably take at HCC.
Yeah, but HCC, it's a multiple, the HCC is usually a semester. That's more than you want. I want to do something where it's like Saturday, we get there at 8 o'clock and we're done by 6, or something like that. And you spend a whole day, you take 2 different breaks and they teach you all the ins and the outs of pottery. You'll make like a pot with, snaking the clay. You'll leave with like a plaque and it's cool. And it's the same people that teach at HCC, by the way. But
What organization are you talking about?
TXRX Labs, Houston, TXRX Labs. I'll take some time to give them a shout out because I want them to be as successful as possible. This one here. These guys.
TXR.
Yeah.
What's the membership fee for if you're already paying for the class?
Oh, now it's cheap. Now it's not like it was then. And it may have even been more than $1,200. I may be underestimating that.
You get all the classes for free?
No, now they're not free classes. They're still like $50, but $50 is $50, but that's not much, So you're in a class with probably like maybe 10 to 15 other people and you're working on this stuff. So like here's the MIG class, right? Let's say this is something I've always wanted to do.
Yeah.
If anyone wants to do the MIG welding with me, give me a shout. But okay, let's do it, So here, this class is $150 for the MIG welding. There's obviously, it's gonna be a more expensive class because it's metal and shit, but I've always wanted to learn how to weld. So they do all that stuff there.
I looked on the website under
It's just
fabrication.
one class session or all the classes?
Well, they do MIG welding and they do TIG welding, and I'd like to do them both. One of them is stick and one of them is,
I'll do
know.
both of them with you.
yeah. The other one's 170. That's gotta be super well worth it though.
Yeah.
I looked under the fabrication tab and it shows the prices for like using the different stuff, and it said the 3D printers I think were free.
Cool.
That's very cool.
I mean, we do free classes. Why the fuck can't they? Especially if it doesn't cost them anything, So yeah, they have been around not nearly as long as HLUG. In fact, I remember when we got into fights with them in the early days.
Really?
Yeah, we did. Not we. I actually sided with them, but I was at Hal PC, and when they were at the Caroline Collective, and they came up to Hal PC, and they wanted to use Hal PC. They wanted to get in with Hal PC. They were looking for a host. And Hal PC was a bunch of old dudes with super gray beards. They were all like Vietnam vets. They wanted no part of it. They were like, oh, where are you gonna put all this metal stuff? You're gonna have metal stuff in an office building? They're like, we needed some space to do it, And eventually they ended up getting an office building, literally. They were a place called the Caroline Collective. It was a fucking office building in the medical center. They had like an oscilloscope in there, and they were teaching Arduino classes. That's actually I was one of the first people in Houston to play with the Arduino there. I built it myself.
How did you pull up the calendar?
I went to the TXRX site and I hit Makerspace classes or Makerspace calendar. There you go. They have both.
Oh, and
Yeah.
Evan,
They have classes there and they have calendar. What's up?
through circumstances which will not describe here, I have come into possession of an oscilloscope.
Cool.
I should bring it. I forget. I'm gonna bring it one of these days.
Cool. I mean, I have one, and I probably don't know how to use it very well compared to these guys. This is their thing. They're hardware hackers, so they do anything with hardware. They can, they have now. They're so damn successful. They have plasma cutters. They have a water jet machine. They were I think the brains and the labor behind Rice competing with the build your car thing. They actually did the whole work there of like making a race car. There was something Rice was competing with it.
Who has the plasma cutter and the...
These guys, and they do classes on it. Look right, let's see here, plasma, there you go, right there.
They have a laser welder,
They have everything.
so I could bring my.
And you know what's also funny about this too? I'll tell you what's really fucking funny about them. Well, first thing, I will say this. Let me say this on the record, and then off the record, I'll say some more. The guy that runs this, his name is Roland, right? He's a very divisive character. He's one of the smartest motherfuckers in Houston. Swear to God, the dude is a fucking, he is a pedestal of go-to guy. You know, like if I had to pick the fucking actual Bear Grylls, it'd be that dude. No one wants to have a conversation with him, but there's not a fucking rut that guy can get himself in he ain't getting himself out of. You know, he gets into a wreck with his car, gets split in half by a fucking, you know, Superman or whatever, he's putting it together himself. He knows everything about anything physical. He's something else just to meet him and like see him work, you know. He's crazy determined. He has like his own beliefs and his own views. He don't want to talk about nothing except hardware and getting things done. What do you want to build? You know, and you tell him, I don't really want to build it, I want to learn it. He's like, nah, fuck that, what do you want to build? He's got his own way of doing things, you know, but he's something else. What's up?
Is it TXRX?
TXRX, the dude's name is Roland. He's a hoot, man. But they used to do something called Pancake Fridays, where you go over there Fridays and they'd actually make pancakes and I help them wash dishes. That was like their thing for a while.
They can bring broken stuff to the welding hall? You don't know, but maybe bring broken stuff and have them fix it 30 minutes. A laser welder, they can fix broken.
They don't just have, they have powder machines there. They have vacuuming machines if you want to learn how to like vacuum produce things. Like the only thing that competes with Shenzhen and Houston is TXRX, where you can take it to one fucking dude who knows how to manufacture anything. They have, but the other funny thing is too, like you ask them where they get their shit, they buy their shit from China. They buy American-made shit from China. I got a tremendous kick out of that. So in the 1960s, America is the manufacturing center of the world. They're making everything, and it's still, to this day, the best shit you can buy, right? So the problem is it's all broken down, it's used, it's old, and they don't have like touch screens on it. And the Chinese make 50 million things that are inferior, but that's how they do things over there. They don't want it anymore. They fucking buy that shit for scrap. They bring it over here, and I was watching them do it. It was crazy. They buy this shit that was made in the 1960s in the Rust Belt from overseas as scrap metal, you know, and then they gut it. They take out like the old joysticks, you know, and the CRT screens, they remove them. They put in LED screens and they put Linux CRC on it. And everything gets running, everything there runs Linux CRC, you know. And that's how they do it. It's got like a touch screen on it running Linux with CRC. But yeah, I mean, they have every kind of tool you want. They have another one that does like it's not like a laser cutter. They had like a demonstration that they were doing one time. I saw them do. And they were trying to get people in on this. How do you get through a safe cleanly? And the safe was made out of tool metal, you know? And they had like, I want to say it was like a metal cable, and it had 30 volts going through it or something like that at a very high amperage, I believe. And they just put the safe in water and they say it's going to cut it in half. It'll take it, a day. A clear cut, you know, come back and it's cleared through it. All kinds of weird shit. It's interesting. Go check it out. But anyway, what I was saying is TXRX, that's where it comes from. So if you go to TXRX Labs, that's where they take their name from. It's send and receive. So TX is always send, RX is always receive, it's everywhere. So the MSPC channel thing, we create a TXRX side of it, and these are things that we can communicate with. We create this new thread. We say TX send, and we give it val, and then we say unwrap, right? What does unwrap do? If the receiver side isn't listening, it's already shut down, the thread has ended, whatever, then you won't be able to send. You'll get an error back. So here's one, and this one we're actually receiving. So we're saying die if we can't send this value, and then we have received saying RX receive. Now what's interesting is this is MPSC, multiple producer, single consumer, and we're only producing one value. Not a very good use of it. Down here we have, again, we are doing a single value. So what's the deal? Why are we doing this twice? Oh, we're showing you that after you send the value, you've moved ownership. So when you send the value, you have actually moved ownership of it. The thing that you've sent it to isn't just getting a copy of it, it's taking ownership of that. Why is that important? Because some people want to think of this as a telephone, where you pick up the telephone and you say, hey, I'm sending you this value. That is a useful way to think about it. except multiple people can have telephones producing the value, so it's MP. And also, you're not actually just sending information about it, you're actually sending the real thing. You got your hand up?
I have a couple questions. First, so the receive function, is it a blocking operation where it will not move until something is sent?
Yes.
And my second question is, I forgot the second question.
Yeah, receive will wait for something to be produced.
I remember the second question.
And if you don't want to wait for something to be produced, what do? Put it in a thread. That's it. You need a solution.
Wait for it, but you're waiting on a separate thing.
That's right. You wait somewhere else. Someone's got to wait for it, right? Because if you have one thread and it's saying I'm producing a value, something literally has to be waiting for that value, or you don't know what to do, right? So it's not like this is a lack of engineering. It's by definition. If one thread says I'm going to produce a value and it's done, something else has got to be waiting for it, you know?
Is there a way to non-blockingly check if there's a pending value?
If there's what?
Like, is there a way to maybe like check, is there a value that's waiting to be received, or, and if not, just keep going and then later on you check again or something?
PRX might have a method. You should have a method like a state, like, well, actually not sending.
I mean, put an atomic to it that says ready, and then flip the flag. And then in a loop, check whether or not the flag is flipped. And when it is, pull the data off. So an atomic happens everywhere at the same time. You can share an atomic with any amount of threads. You can use an atomic to work as a semaphore. This is ready to be received. Otherwise, you just loop until it's ready.
My second question was...
But you would never do that. You'd always use Tokyo. So I'm telling you how you would always use Tokyo or something like that.
So this, since it's multiple producer, does it work like a queue?
Does it work like a queue? Kind of, but you can never have a line of items. You know,
So what happens if you have, like you receive 3 values, and then you have a single consumer that might be taking longer? Do you lose the values that it can't take? Or?
No, then it blocks on sending them. It's blocking both ways. If something tries to send a value and the other guy's not ready, it's blocked. If something tries to receive a value and nothing is sent one, it's blocked. That's the way I recall it. We can look that up though here. The receiver has 2 useful methods, recv and try receive. Okay. With recv, short for receive, it'll block the main thread's execution and wait until a value is sent down the channel. Once a value is sent, receive will return a result TE, right? The case in which the E is in the event that the thing died in transmission or something.
Try to receive is what I was asking for.
Yeah. Which I didn't even know existed because I've never wanted that. You know, at the point that I'm doing this, I always, as they're producing values, I have nothing else to do. You know, I'm not saying that always has to be the case, but generally I say there's 5 different things, go produce values, and I'm waiting for one of them to produce a value. There's nothing else I have to do. I'm the orchestrator, I'm the server. They're out there doing my workload, running jobs. The try receive method doesn't block, but it will instead return a result TE immediately, an OK value holding a message if one is available, and an error value if there aren't any messages at this time. So there you go. Rather than having a semaphore, you can use this, and I wouldn't be shocked entirely if this didn't use a semaphore under the hood with an atomic. You know, so we can go look at that source code later if you want. Channels and ownership transference. The ownership rules play a vital role in message sending. Am I there? Yes, I'm there. Okay. The ownership rules play a vital role in message sending because they help you write safe concurrent code. Preventing errors in concurrent programming is the advantage of thinking about ownership throughout your Rust programs. Okay. String from high, text value, unwrap. Here we print val after we sent it down the channel with tx send. Okay. Nothing new here. They are effectively showing you that yeah, but they're showing that you can't do this, right? Because after you send it, you've lost ownership of it. So you can't print it afterward because you no longer have ownership. Sending multiple values and seeing the receiver wait. So this is to get to what you're talking about. Here we have multiple values, high from the thread. We try to send each value, and we are effectively watching them here. For each value in vals, tx send value unwrap, and then we're waiting 1 second. So this is actually blocking, and it's waiting for that second to be done so it sends another value. And it just so happens that I think most of the use cases that's totally acceptable. What else are you going to do when you're writing something that is literally the receiving side of it and nothing is sent? Generally, what that tells you to do is spin off more workers, right? So let's say that you're calling Amazon and you have 5 different workers and they're still not sending data fast enough for you. What are you going to do? Next time, send 10, you know? And if 10 gets you blacklisted, what are you going to do? You're going to use SOX 5 on a proxy on one of them, on another set of them, and send 10 more. And if you're still waiting, what are you going to do? Get another SOX 5 proxy and send 10 more. You know?
One use case that I can think of is, you mentioned before, a timeout. I could do a timeout by constantly try, receive, and then when there's like enough time passed, I just get out of my loop or something. Or we try and
I'm sorry, get out of your what?
like a timeout, like I could on a loop try receive.
Right?
And after trying receiving, kind of like count how long it's been to do a timeout function or something.
Sure, but you could also just block, and then when you wake up, see what the time is. And then when you finish your work, store the time, and then hit back to the blocking function. And when you wake up, compare the time.
But what if you never ever receive, then you're blocked until you receive something, right?
You're blocked until you receive something.
But if you want to time out the receiving side, if it's taking longer than 5 seconds.
Sure, that would make sense, yeah. But you'd have to know where the receiving side is. The point of MSPC is that you have them producing the content for you. If you want to be able to communicate back with them, then you're going to actually have to track it. You're probably going to want to do single-way communication. So you're probably going to want to tie the join handle to a one-way receptor that can receive your signal to die, and then it sends its response back to you. So you have to build two-way communication in there, you know?
And if you have multiple threads receiving, you need the multiple consumer version?
No, there's no multiple consumer version. But one thing that I would say is that the timeout can also be done inside the thread, right? You don't have to be the parent that's watching the thread. There are methods for the thread to time out itself. Right? So that's easier. You're not the first one to skin the cat on timing things out. That's a solved problem, you know? So you can just use Tokyo and tell it that you want to time out the request. It's very easy. In fact, if you just use REQWEST, right down here, latest, right down there, client builder timeout, enables a total request timeout. So again, the whole unit system is unified behind Tokyo. You use Tokyo on it, you can time it out very easy. And Tokyo is faster for doing this anyway. You would never, I'm telling you what you can use threads for, but you'd be foolish to build a threaded system that was doing this thing with Amazon. You would just use Tokyo and it would take care of all of it. Balancing it would be an option you could set, all that kind of stuff. And it would be way faster and more efficient. Okay.
If you have received multiple threads, when you send, do both receive or just whichever is faster?
If you have multiple threads
That have received and you send something.
I don't think that there is this concept of multiple receivers. You keep saying that. Let's see here, MSPC.
Oh, yes. Yeah, because I guess you need to give ownership to the thread for the receipt, right?
Let's see, what you would be talking about is multiple producers, multiple consumers, right? There you go. So there is someone who built it. Concurrent queue. This trait provides concurrent queues that can be shared among threads, array queue and seg queue, an unbounded MP-MC queue that allocates small buffer segments on demand. Or this one. I don't know. The point is that you're talking about a very special workload at this point. Let's finish this. Where am I at here? Did we finish this chapter? We did. Did we finish this chapter? No. Okay. Shared state concurrently. Mutexes allow access to data from one thread at a time. Okay. So we talked about when we use ref cell, we need to stop multiple things from having, when we use RC, we need, wait. Yes, when we use ref cell, we need to stop multiple things from having mutable access to the thing that it has. Ref cell allows to say you can have as many immutable variables, immutable copies of this, or references to this as you want, or one mutable copy. That's the trick that ref cell does, and it does that in runtime. Ref cell doesn't work across threads. So how do you make it work across threads? Use this thing called mutex. Mutex says, I have this block of memory and only one thing can access it at the same time, right? So it's a mutable block of memory that only one thing can access. It works just like the heap in a way, but it controls access to it behind a mutex guard. So a mutex guard is this thing, think of it like a thing on a box, and it says you can have one thing writing to that box at a time, or as many things reading from that box at a time. Now, a mutex is slightly different in that I think it's one thing reading from it too. One thing reading or writing to it is a mutex. So in Rust, you have this mutex, which is multi-threaded. One thing has exclusive access to it, reading or writing. I'm going to correct that. Reading or writing, one thing has exclusive access to it. There's also something called, I forget the name of it now. I'll think of it in a second. What? No. Rust, mutex with multiple, I think it's called RW lock. RW lock is a mutex that allows multiple things to read from it, one thing to write from it. So RW lock is actually the close analog to ref cell that works on multiple threads. Mutex is exclusive access. So a mutex means only one thing can read or write to that memory at the time. Ref cell is more sophisticated but allows multiple things to read from it. So you have this mutex, which is going to control a piece of memory, allow you to share it across multiple threads and have one thing read to it or write from it at the same time. That is tremendously useful because now you can have multiple different threads doing this work, contacting Amazon, processing the web page, but when they're writing their result, you may want them all to write the result to the same block of memory. And now you have a way to share that memory with all of them. The only problem is only one of them can write to it at the same time. So what do the others do when they want to write to it? They block, they wait. And then that thing that is writing to it, when it's done, it will free the block and something else can take it. Free the lock and something else can take it. Now, here's the thing about it. When nothing frees the lock, what do you have? You have what they call a deadlock, right? This is a really bad problem in program design, a very old one too. So the deadlock is effectively when you have something didn't free the lock and now everything is waiting on it. Your whole system is doing nothing, right? And it's possible to do that. So here's a mutex. We have a mutex for 5. We're storing 5 in a mutex and we're saying it equals M. M is the mutex. And then we do M lock unwrap. This gives us the ability to write to that location. Now we have unlocked it. That locking is blocking. So if something else has a lock, we're going to wait for that call. Then after we have access to that piece of memory, we can assign to it. We say set it equal to 6. Now, after this is done, the scope is done, what's going to happen? That m.lock is called the mutex guard. It'll no longer need to be owned because it's going to be freed. And when it's freed, the lock is released. And another thread can use it. Here's how you share a mutex with multiple threads. So here, in this one, we're doing this for underscore in 0.10. We're spawning 10 different threads here. And each one of them is trying to lock the same thing at the same time. And each one of them, when it locks it, is going to dereference the value of number, that piece of memory, and try to increment it by 1. But because they're all doing a lock on it, you know it's going to be consistent with what you'd expect. Now, if you were to write the same thing in C, right, and you were not to do the mutex, you didn't write that in there, what would happen? You could get any number. Why? Because you could have out of order writing. Right? The mutex promises you don't have out of order writing. The first thing that tries to lock it's going to get the lock, then everything else is going to wait on it. And because everything that's waiting is doing the same thing, incrementing it by 1, when the lock is released, the next one will hit. It'll increment it by 1, then that'll give the lock up to the next thing. Then it'll hit, it'll give it up to the next thing. In C, they could all hit the memory location at the same time, all read the value as 0, and all write the value as 1. So this is why Rust is saving your ass here. It has this type of stuff built in. But in C, nothing stops this. All of those different threads can write to the same piece of memory, literally at the same time. Right? Okay. So this saying it doesn't exactly work like this, and why doesn't it work? It doesn't work because okay. Okay, so the mutex, which is controlling that memory, right? You have to have an ability to share it with different threads. So they're gonna show you that this doesn't work because the mutex has to be shared with different threads. So how do you share it with different threads? They're gonna show you RC. RC doesn't actually work for this. You have to use ARC, ARC, right? Which is right here, atomic reference counting with ARC. We went over this briefly when we went over RCs. I said, with single-threaded applications, you tend to use RC ref cell almost all the time in that order. You very seldom use a ref cell of an RC. In the case of a vector, we did that. We saw that one example in this class today. But generally, you see RC ref cell because you need to share something that has interior mutability. With a mutex, it's protecting against interior mutability, right? I made the analogy between ref cell and mutex. Mutex protects against interior mutability by saying one thing can have exclusive access to me. One thing can have exclusive access to that block of memory. In the same way that ref cell says one thing can have mutable access to this block of memory, right? But what it doesn't allow is multiple threads to share that ability to get that, right? So how do you share it? With ref cell, you share it by using RC. That's what allows you to share that ability to get someone to have writable access to that memory. You share it with RC. With mutex, you share it with an ARC, an atomic reference counter, right? So we went over that earlier. I said there are different ways of having threads communicate with each other. One of those methods is an ARC, atomically reference counted variable. This is a special piece of data on the processor that guarantees nothing else has accessed it in between your operation. So when you say you want to increment something that's atomically reference counted, you tell your processor you want to do it, there is no delay between the read operation and the write operation because the processor has implemented both of those as a single operation. Normally, when you say you want to increment a variable, one thing reads it, another thing writes it. And when you have multiple threads and they all have different cores that are instructing it, multiple things can read it and multiple things can write it. With an ARC, you have one operation and it works for all of the cores. It says, when I run this operation, I'm reading and writing to it at the same time.
It's similar to the concept of transactions when it comes to...
Kind of. You can think of an atomic as a processor's transaction safe unit. Yes. It's a transaction in the sense that underneath the hood in the processor, there's different things going on. But for you, it's just an ARC operation. This is an actual method of declaring a variable as such and getting a different instruction set. So there's something here, if you x86 intrinsics. Probably misspelling that, but who cares? Stupid word anyway. So you see these operations here? Just to give you an idea. These operations are the assembly instructions for intrinsics. They're all different. You add something with x86 by just calling add L, add left, add right. They have like 64, add 64, 32, that kind of stuff. But if you look here, this is crazy complex. These are the intrinsic operations.
So those are like the ones that you do between registers and stuff.
Those are what's actually happening when you're using an arc in Rust. When you're using an arc in Rust and you want to do something like increment, right? What it's actually going to call under the hood is something like this. Let's find the one that doesn't have the underscore, if it exists.
Yeah, but what I mean is like, you know how like on C terms, when you have CPU, you have the ALU, the logic units.
The ALU, yes. What about the ALU?
So these are things that are implemented in the CPU.
These are things that are implemented in the CPU, yes. That's interesting. I would have expected that to show up. Okay, there you go. Add carry 8. I don't know why they're not on the Intel page. That's kind of weird.
You didn't search for add.
Well, I also didn't know to search for add, but how come I found it on the... They're not there. Okay, they have add carry U32, 64 or whatever. Okay, so they call them something different. But this is... I don't know the answer to this. This is something else I have to look up. Anyway, good question. Or inability to show that right now.
It's 9.
Is it 9? All right, so what are we at? We're at... we're here. We're at 16.3. Extensible concerted sync concentrates. Okay, this is very easy. Good. This is one page. We're at the end of it. I already told you, send means you can take something and transfer ownership of it across threads. Sync is effectively being able to transfer access to it by reference across threads. Some things you can do that to, some things you can't. Almost every type in Rust is send. There are some exceptions, including RCT. Remember, we said RC cannot be sent across threads. So what do we use in place of it? ARC. Why? Because RC is using an integer and ARC is using an atomic integer, right? When it comes to things that are sync, any type that is send, I think there are some exceptions to it. Any type that is send, a reference to it is sync, is usually the way it says. Yeah, in other words, any type T that is sync, wait, the sync, let me read this their way. The sync marker trait indicates a type is safe for implementing sync to be referenced for multiple threads. In other words, any type T is sync if a reference to T and a mutable reference to T is send. Meaning the reference can be sent safely to another thread. Similar to send, primitive types are sync, and types composed entirely of types that are sync are also sync. Okay, read this chapter. These are just about the traits and how the magic works under the hood. This is how the cake gets made, so to speak. And you'll see how these two traits allow you to do really cool things with Rust and parallelism and concurrency. But that's the point. The point that I want to drive home is that the same tricks we have been learning early on, that is the application of that really makes it worth it is when you get into this stuff. Because it makes it more difficult to do all the easy things. But when you get to this kind of stuff, it is way more realistic that you figure it out. And this is the kind of stuff that pays a lot more money, you know? The hello worlds are not going to make you money. So if it's a little bit more difficult on that end, you'll figure it out. But you get into this kind of stuff, and that's where the money's at.